The universe stretches before the mind like an endless ocean. Its waves rise and fall without count, without origin, without destination. No shoreline frames it, no first ripple breaks its silence, no final tide withdraws into stillness. To gaze upon this immensity is to confront a riddle that dissolves language itself. If time has neither beginning nor end, what does it mean to exist within it? For as long as memory can reach, humanity has clung to stories of origin. From ancient firesides to modern laboratories, there has always been a need to mark the first page, the opening line, the primal spark. Creation myths promised a dawn of all things, a moment when silence fractured into light. Even modern science, armed with equations and telescopes, sought the instant of birth, a singular flash called the Big Bang. Yet behind each theory, each story, rests the same unspoken assumption that there must have been a beginning. But what if that question is itself a mistake? What if there was never a genesis, never a first breath? In an eternal universe, time does not march from a single point. It coils, flows, or simply is, without source or conclusion. Beginnings lend stories their meaning. Endings give them weight. To strip both away leaves a silence more unsettling than any explosion of creation. Could the cosmos itself be a cycle without origin, a truth older than any myth? And if so, what becomes of human longing for purpose, for closure, for a frame, to hold the picture of existence? In the stillness between galaxies, the possibility lingers like a whisper. Perhaps there was no first dawn, and perhaps there will be no final dusk, only the endless ocean of being, stretching forever. If you wish to journey further into the mysteries of the cosmos, to trace the echoes of time and explore the infinite expanse of space, subscribe and join us. Let each revelation, each whisper of the universe unfold with you, as together we chase the questions that have no end in the earliest attempts to understand existence. Before telescopes traced galaxies across the night, human imagination turned to story. Civilizations crafted myths not as ornaments of belief, but as architectures of meaning. In the hymns of the Rig Veda, the cosmos stretched back without origin, a breathless eternity where cycles of creation and dissolution rose and fell like tides. Upon an infinite shore, ancient Hindu cosmology imagined time as vast ugas, epochs, recurring endlessly. Each universe dissolved only to be born again, as if the cosmos were a great breathing, without beginning and without end. In the philosophy of the Stoics too, the world was eternal, bound to a rhythm of conflagrations and renewals. Universes rising from fire only to return to flame. Aristotle, gazing at the heavens, reasoned that motion itself was eternal, that the cosmos could never have been born, for nothing could arise from absolute nothingness. To him, the stars were eternal fires embedded in crystalline spheres, turning, without rest, guardians of a universe without first moment. Yet, in other traditions, a different vision held sway. The book of Genesis declared a moment of origin in the beginning, a singular act of creation where time itself was, ignited by divine command. This duality of imagination, eternal cycles versus singular creation, shaped human thought for millennia. The cosmos became not just a place of stars, but a mirror for the deepest fears and hopes. Was reality endless, or did it spring from a moment outside time? By the dawn of modern science, these questions were pressed into mathematics and observation. Astronomers of the 19th century, armed with new instruments, believed the universe to be eternal and unchanging. Stars burned without history, scattered across a static stage. The steady-state idea, though unnamed, then lingered as the natural assumption that the universe simply was, neither born nor destined to die. When Einstein turned his attention to the cosmos in 1917, his equations of general relativity held a troubling implication. Left untouched, they predicted either collapse under gravity or expansion into the void. Neither outcome fit the eternal stillness he and most of his contemporaries expected. To preserve stability, Einstein introduced a new element, the cosmological constant, a repulsive force woven into the fabric of space-time, a mathematical scaffold to keep the universe eternal, balanced, unmoving. Later he would call it his greatest blunder, but at that moment it was a defense against the unbearable thought that the universe might be dynamic, that it might have had a beginning. Infinity troubled not only mathematics but also philosophy. An eternal universe promised safety, yet it also haunted the imagination. If time stretched without origin, what meaning could human life hold, flickering briefly in an endless procession? If there was no first moment, could there be true progress, true story, true direction? In the silence between equations, this discomfort lingered like an unspoken shadow. Then, in the 1920s, the heavens shifted. Edwin Hubble, peering through the 100-inch Hooker telescope on Mount Wilson, measured the light of distant galaxies. Their spectra were stretched toward the red, not by accident, but by motion. Space itself was expanding, carrying galaxies away like driftwood upon a swelling tide. The universe was not static. It was not eternal in the way Aristotle had imagined. It was alive with movement, with change. This discovery struck at the heart of millennia of assumption. If galaxies were fleeing, then they must once have been closer, long ago. Rewind the expansion, and all matter, all energy, converges toward a single state, a beginning. The eternal stage crumbled, replaced by a vision of cosmic history unfolding from a primordial event. It was Georges Lemaitre, a Belgian priest and physicist, who gave this vision form. In 1931, he proposed the universe began as a primeval atom, a single point of unimaginable density which fractured into expansion. What others saw as heresy against the eternal cosmos, he described as the birth of space and time themselves. From a singular moment, everything emerged: galaxies, stars, life, consciousness. The question of beginnings, once the province of myth and scripture, had entered the realm of physics. Yet behind the elegance of this new narrative, unease persisted. Could everything truly emerge from a single moment? Could time itself be born as though from nothing? The universe seemed to whisper to contradictory truths, that it might be eternal, without edges, and that it might have sprung from a singular genesis. Between these opposing visions, modern cosmology began its restless journey. The announcement of an expanding universe did not fall into silence. It collided with centuries of thought, unsettling the foundations of philosophy and science alike. For generations, scholars had assumed that eternity was the natural backdrop of existence, a stage so vast and permanent that human lives, stars, and even galaxies would come and go without leaving a trace upon its fabric. To declare that this stage itself had once been compacted, compressed into something finite, was almost unthinkable. It implied that the universe had a history, that it had a childhood, and perhaps, by extension, that it might also have an end. The steady-state dream, the comforting vision of a cosmos immune to change, fractured under the weight of Hubble's evidence. Among scientists, the reaction was not uniform. Some resisted fiercely, clinging to the eternal model. Fred Hoyle, Thomas Gold, and Herman Bondi would later defend the steady-state theory with elegance and conviction, insisting that as the universe expanded, new matter must simply appear to fill the growing void, keeping density constant and eternity intact. Hoyle, in fact, gave the rival theory its now famous name, the Big Bang, meant as a derisive mockery, a way of painting the idea as childish, even absurd. Others, however, felt the shift as a revelation. Lemaitre's primeval atom was no mere theological echo, but a profound scientific proposition rooted in relativity and observation. For the first time, humanity faced the possibility that not just stars, but time itself had once been born. Einstein himself was slow to accept this vision. For years he preferred the elegance of balance, the notion that the universe was eternal, held in fragile harmony. Yet as Hubble's data grew undeniable, he abandoned his cosmological constant, confessing the static model to be untenable. The shock of this concession reverberated beyond physics. If even Einstein's carefully tuned equations bent toward a beginning, perhaps the cosmos truly was more fragile, more dynamic, more fleeting than philosophers had dared to imagine. Still, questions lingered. If the universe had a beginning, what mechanism ignited it? Could something arise from nothing, or did the word nothing itself collapse in the face of such a question? These uncertainties became fertile ground for debate, not just among scientists, but within culture itself. Religious institutions saw in the Big Bang a vindication of creation stories, a scientific echo of let there be light. Skeptics countered that the theory raised more questions than it answered, that invoking a first moment merely displaced the mystery further back. What came before? As the 20th century pressed forward, the divide sharpened between those who embraced the Big Bang as the universe's birth certificate and those who searched for ways to preserve eternity. The discovery of the cosmic microwave background radiation in 1965 would eventually tilt the balance decisively. But in these early years, the struggle was not only scientific, but existential. Humanity was being asked to let go of the timeless ocean and accept instead a river with a source, a river that might one day run dry. For many, the transition was exhilarating. For others, it was unsettling, even unbearable. The origins of the discovery, then, were not a single moment, but a cascade of revelations, doubts, and philosophical reckonings, from the chants of ancient priests to the calculations of modern physicists. The question of eternity versus beginning refused to be silenced, and in that refusal, the mystery only deepened. If the universe truly did have a birth, then what lay beyond that moment, before light itself, in the silence where time had not yet begun? The first whispers of a universe with a beginning were met not with wonder, but with resistance. For generations, the cosmos had been imagined as a stage without construction or decay, a steady and unbroken backdrop upon which stars and galaxies played their roles. To suggest that this stage itself had been born, that there was a first moment, seemed to many a distortion of science itself. When Georges Lemaitre advanced the notion of a primeval atom, the reaction was cautious, sometimes derisive. Fred Hoyle, decades later, would voice this skepticism with characteristic sharpness. On a 1949 radio broadcast, he mocked the idea as the Big Bang, a phrase meant to belittle it as crude and theatrical, unworthy of serious consideration. Yet the name, meant as dismissal, became immortal. At the heart of this rejection lay not just scientific doubt, but philosophical discomfort. The steady-state theory, defended by Hoyle, Hermann Bondi, and Thomas Gold, offered a picture of eternal balance. As galaxies drifted apart, new matter would emerge to fill the widening void, ensuring the cosmos looked the same in every epoch. It was elegant, symmetrical, and eternal. A universe without birth, without death, free from the unsettling notion of a beginning. To many, it felt safer, almost humane, because it preserved continuity in a way the Big Bang could not. But science is shaped as much by its age as by its instruments. In the shadow of the Second World War and the onset of the Cold War, the stakes of cosmology were sharpened. A universe with a beginning echoed too closely the language of creation, raising uncomfortable parallels with theology. Some feared that a scientific admission of a cosmic genesis would hand ammunition to religious institutions, blurring the boundary between empirical inquiry and faith. Others, however, saw in it a rare harmony, a reconciliation between the spiritual and the scientific. The debate was not confined to laboratories and observatories. It seeped into culture, into politics, into the philosophy of existence itself. Einstein, who had once bent his own equations to preserve a static cosmos, slowly shifted as evidence for expansion mounted. Meeting Lemaître in 1933, he acknowledged the priest-physicist's vision, declaring, "This is the most beautiful and satisfactory explanation of creation to which I've ever listened." It was a reluctant concession from a man who had once dismissed the idea as abominable. The weight of Hubble's data, and the inexorable mathematics of relativity, pulled even the most skeptical minds toward the possibility that time itself had a boundary. Yet the human reaction went deeper than equations. The thought of a singular origin carried with it a fragility that unsettled the imagination. An eternal universe promised permanence. It allowed human existence, however fleeting, to rest upon a foundation without cracks. But a universe with a beginning implied vulnerability. If there had been a first moment, there might also be a final one. Existence itself began to look like a story, fragile and finite, bookended by forces beyond comprehension. The eternal ocean was gone, replaced by a river with source and mouth. And humanity found itself caught in the current dot. This collision of visions, eternal balance versus explosive birth, became one of the great intellectual dramas of the 20th century. It was not merely about data points or telescopic readings, but about the human relationship to time, to infinity, to meaning itself. For some, the Big Bang was a doorway into profound mystery, a recognition that existence had a history. For others, it was too much like a mirror of theology, a scientific betrayal of the timeless. Between faith and reason, comfort and unease, the universe itself became the battlefield of ideas. And yet, beneath the clash of theories, the cosmos continued, its silent expansion indifferent to the quarrels of those who gazed upon it. The truth, whatever it was, lay not in human preference, but in the deep structure of space and time, waiting for instruments, for mathematics, for imagination bold enough to follow its trail. The first reactions were resistance, skepticism, even ridicule, but the mystery was only beginning to unfold. The skepticism of the early decades did not silence inquiry. Instead, it pushed astronomers and physicists to search for traces, for fossils left imprinted in the fabric of space itself. If the universe truly had a beginning, then somewhere, scattered across the cosmos, there must be echoes of that moment, shadows that science could detect. The expanding universe was one clue, but it was not enough. Expansion could be imagined as eternal, stretching back without origin. What was needed was a fingerprint, a remnant of the fire itself, something that could not be mistaken for the workings of an eternal cosmos. The search for such evidence unfolded in the mid-20th century with a new intensity. Scientists turned their eyes not only to galaxies, but to the very radiation that bathed the universe. Theoretical physicists like George Gamow, Ralph Alpha, and Robert Herman proposed in the late 1940s that if the cosmos began as an unimaginably hot, dense state, then the residue of that heat should still linger, cooled by expansion but never fully erased. They predicted a faint afterglow, a sea of microwave radiation filling all of space, a cosmic ember left from the first fire. It was an idea so bold, so poetic, that it sounded almost like myth translated into physics, a whisper of creation, carried endlessly forward through time. The prediction lay dormant for years, largely ignored, as many still clung to the steady-state model. But the tide was shifting. New telescopes, new detectors, and new mathematics were refining humanity's ability to listen to the cosmos. In 1965, quite by accident, two radio engineers at Bell Labs, Arno Penzias and Robert Wilson, stumbled upon a persistent hiss in their antenna, a noise that refused to vanish no matter how carefully they calibrated their instruments. They cleaned the equipment, chased away pigeons nesting inside the receiver, but the signal remained. Unbeknownst to them, they had detected the very afterglow Gamow and his colleagues had predicted. The cosmic microwave background had revealed itself, faint and uniform, a relic of the first light. That discovery shattered the balance of cosmological debate. The steady-state theory, elegant in its refusal of beginnings, could not account for such a fossil. The universe was not eternal in the way Hoyle and Bondi had envisioned. It bore scars of a birth, a moment when energy and matter erupted into existence. The afterglow was not myth, not metaphor, but data etched across the sky. To many, it was the most profound confirmation that the universe had indeed been born. Yet the discovery raised as many questions as it answered. The radiation was astonishingly smooth, almost too smooth. If the universe had erupted chaotically, why was the afterglow so uniform across billions of light years? Tiny fluctuations were present, subtle ripples that hinted at the seeds of galaxies, but the overall calmness of the background demanded explanation. Out of this puzzle, the theory of cosmic inflation was born. The idea that in the first fraction of a second, the universe expanded faster than light, stretching irregularities into uniformity. It was a radical suggestion, a bridge between quantum physics and cosmology, and it carried with it the possibility that the universe might not simply have a beginning, but an origin rooted in forces beyond imagination. The human response to these revelations was complex. Awe at the precision of discovery mingled with unease at what it implied. If the universe had truly begun in a single burst, what preceded it? Was there a before at all, or did time itself emerge in that moment? Each answer deepened the mystery rather than dissolving it. The early investigations, once aimed at disproving beginnings, had instead unveiled evidence that could not be ignored. The universe carried within it a memory, written in radiation, of an origin both undeniable and incomprehensible, and so the question sharpened. Science had uncovered relics of a first moment, but the more it revealed, the more fragile the notion of beginning became. The smoothness of the afterglow, the unexplained violence of inflation, the silence of what might have come before, these became the contours of a new mystery. What had started as skepticism and ridicule was now transforming into reverence and doubt of a deeper kind. The universe was no longer static, nor was it fully understood. It had a history, but one wrapped in paradox. A story whose first chapter remained unreadable. The earliest investigations into the origin of the cosmos began not with certainty, but with the careful search for relics, the faint fossils of creation that might still linger in the night sky. Galaxies, scattered like jewels across the void, became more than points of light. They were treated as historical records, carrying within their light the signature of time itself. The stretching of their spectra, measured with precision, revealed that space was not still but expanding, carrying them away as if borne upon an invisible tide. This redshift became one of the first clues that the universe had a history, that its present form could be traced backward into something smaller, denser, more primal. Yet redshift alone did not answer the question of beginnings. It was evidence of expansion, not of a moment of birth. For that, scientists needed to search deeper into the hidden traces of fire that expansion might have left behind. Mathematics became their tool, a way to peer into conditions too extreme for any telescope to reach. Working in the late 1940s, George Gamow and his collaborators Ralph Alpher and Robert Herman pursued a daring line of reasoning. If the universe had once been unimaginably hot and dense, then the radiation of that epoch should still exist, diffused and cooled by billions of years of expansion. It would not be visible to the human eye, but it would bathe all of space in the microwave spectrum, a faint afterglow of the first fire. They even attempted to predict its temperature, suggesting it would linger just a few degrees above absolute zero. In their equations, the past was not gone. It was written into the fabric of the cosmos, waiting for detection. For years, their prediction remained little more than an elegant idea. Few paid attention, as the steady-state model still held sway among many physicists, promising an eternal cosmos with no need for primordial fire. But then, in 1965, the universe revealed its memory. Arno Penzias and Robert Wilson, engineers at Bell Laboratories in New Jersey, were testing a sensitive radio antenna designed for satellite communication. No matter how carefully they adjusted it, they encountered a persistent background hiss, a noise that refused to vanish. They cleaned the instrument, removed nesting pigeons, recalibrated every wire, yet the signal remained steady, uniform, arriving from every direction. What they had found, without seeking it, was the cosmic microwave background. The very echo of the universe's first light was whispering into their detector, a remnant of a moment nearly 14 billion years past. Simultaneously, across town, a group of Princeton physicists, led by Robert Dick, had been preparing to search for the very same signal, guided by Gamow's prediction. When the two groups connected, realization dawned. The faint hiss was not noise, but the birth cry of the cosmos itself, still reverberating across the heavens. This discovery shifted the balance of cosmology irreversibly. The steady-state model could not account for a universal background of radiation. The Big Bang, once ridiculed, now stood upon the firm ground of observation. The universe had left behind a fossil not of matter, but of light, a perfect backdrop, against which the story of everything had unfolded. That light was not merely a confirmation of expansion, it was a window into the very first seconds, a reminder that time itself had a horizon. Yet the emotional resonance of this moment extended beyond physics. For centuries, humanity had asked whether there was a first spark, a beginning to existence itself. Myths had told of divine fire, sacred breath, or cosmic eggs from which the universe was born. Now science, with its instruments of metal and mathematics, had discovered something uncannily similar, not in poetry, but in data. The confirmation carried both exhilaration and unease. To know there had been a beginning was to confront mystery on an even greater scale. What ignited that first light? What came before it, if before had meaning at all? In the hiss of static, the universe confessed that it had not always been as it is. The cosmos bore scars of a birth imprinted upon the sky itself. Humanity had long desired confirmation, proof that the story of existence had a first page. In the faint radiation of the cosmic microwave background, that proof had been found. And yet, as so often in science, the answer only opened a deeper question: what lies beyond the first spark? The revelation of the cosmic microwave background transformed cosmology from speculation into a field anchored by empirical evidence. Yet the true depth of its meaning only unfolded slowly. The radiation was not uniform in a trivial sense. It carried with it the faintest fluctuations, variations so small they seemed almost imperceptible. To the naked eye, the sky appeared smooth, but hidden within this relic glow were the seeds of all later structure, the whisper of galaxies, stars, and planets that would one day form. At first, instruments were too crude to detect such subtle patterns, and the background appeared as a simple, even veil, but already scientists understood what it implied. The afterglow was not just a fossil, it was a time capsule, carrying information from when the universe was less than 400,000 years old, a child in cosmic terms. To study it would be to reach backward almost to the beginning, into the very architecture of creation. For the steady-state model, this discovery was catastrophic. Its promise of eternal balance could not explain a universal bath of ancient light. Fred Hoyle, who had once coined Big Bang as a term of mockery, now found his own theory receding into the shadows. The universe had betrayed him, leaving behind evidence too strong to ignore. Even Einstein's old cosmological constant, once a device to maintain static eternity, had been replaced by expansion, by dynamism, by evolution. With the cosmic microwave background, the Big Bang was no longer merely plausible. It was unavoidable. A universe that had once seemed timeless was now revealed as a narrative with chapters, with a clear beginning etched in fire. But for humanity, this shift was more than scientific. It was existential. A cosmos without origin could be seen as comforting. A grand eternal stage upon which life appeared briefly but without disturbing the deeper fabric. Such a view offered security, a sense that the universe was immune to the fragility that haunted mortal minds. But a cosmos with a beginning was more unsettling. It suggested not only a start, but perhaps an end. If the universe had erupted into being, it could also fade, collapse, or dissolve into silence. The cosmic microwave background thus carried both revelation and unease, a reminder that existence itself was precarious, born from a single fragile spark. As the discovery settled into the foundation of science, one question became unavoidable. If this was the echo of a beginning, then what was that beginning? The physics of expansion, of nucleosynthesis, of cooling plasma all explained what happened after the first moments. But what of the origin itself? What ignited the great eruption? The faint glow revealed that the cosmos had not always been here, but it gave no answer to the mystery of why it began. Humanity had pulled back the veil of time and glimpsed its earliest trace, but beyond it lay an abyss of silence. The hiss of Penzias and Wilson's antenna was thus not an ending, but a new beginning for human thought. It demanded instruments more precise, theories more daring, and imagination willing to peer into the furnace of the first second. In the decades to come, satellites would map the microwave background with exquisite detail, and entire new fields of cosmology would emerge to explain its cryptic patterns. But in that first moment, as two engineers puzzled over an inexplicable noise, the universe had spoken. It had confessed that it was not eternal, not unchanging, but a story, and stories have beginnings. The discovery of the cosmic microwave background had opened a door, but what lay beyond it was still cloaked in haze. For years, cosmologists had stared into the faint afterglow of creation, straining their instruments, listening for whispers hidden beneath the static. By the late 20th century, the time had come to sharpen the view. In 1989, NASA launched the Cosmic Background Explorer, COBE, a satellite designed not to look at stars or galaxies, but to gaze into the sky itself, into the silent ocean of ancient radiation that flooded every direction. What it found was astonishing. The glow of the universe was almost perfectly smooth, an elegant bath of microwaves stretched across space with a precision that seemed unnatural. Yet it was not flawless. COBE's detectors revealed the tiniest irregularities, fluctuations in temperature 1 part in 100,000, ripples faint yet profound. Those ripples were not mere noise. They were the fingerprints of the first structures, the faint blueprint from which galaxies, stars, and planets would eventually rise. The map COBE delivered to humanity was not a static image, but a revelation. The universe had not only a beginning, but an order, a pattern etched into its very birth. 2 decades later, WMAP refined this vision, sharpening the contours, tracing the faint tapestry of hot and cold spots across the sky. And then came Planck, whose detectors in the frozen quiet of deep space captured the afterglow in exquisite detail, transforming the static hiss of Penzias and Wilson into a cosmic portrait with astonishing clarity. With each mission, the relic radiation became less of a blur and more of a storybook, a story not only of light, but of the geometry of space, the density of matter, the curvature of time itself. Yet this precision unveiled a deeper mystery. The universe, as revealed by the CMB, was both astonishingly uniform and subtly imperfect. The smoothness was perplexing. How could regions of the sky, separated by vast gulfs of space, too large for light ever to have crossed between them, look so nearly identical? How could a cosmos born in chaos carry such seamless harmony? Out of this puzzle arose the idea of cosmic inflation, a bold hypothesis suggesting that, in the first unimaginably brief fraction of a second, the universe expanded faster than the speed of light itself, smoothing out its wrinkles while planting the seeds of later structure. Inflation explained the uniformity, the ripples, even the large-scale geometry of the cosmos. It was elegant, powerful, and terrifying in its implications. If true, it meant the universe had not merely exploded into being, but had surged in a violent exhalation that stretched reality itself beyond comprehension. But inflation also pushed cosmology toward its philosophical edge. To speak of the first trillionth of a second was to speak of a domain where classical physics began to collapse. General relativity described the geometry of space and time, the bending of light, the birth of singularities, regions where equations diverged, where infinities loomed. Black holes offered a haunting analogy. Within their horizons, relativity, predicted a point where time itself ended, a singularity in which the laws of physics broke down. If black holes contained such boundaries of understanding, could the universe itself have begun with one? The Big Bang, viewed through the lens of relativity, looked less like an explosion and more like a singularity of all existence, a place where time was not defined, where before carried no meaning, yet quantum theory told a different story. In its world, uncertainty was the law. Particles flickered in and out of being, and the vacuum was alive with restless possibility. The smoothness of the cosmic microwave background hinted at quantum fluctuations stretched across the infant universe, magnified by inflation into the galaxies of today. What began as microscopic randomness had been inflated into the grand architecture of the cosmos. In this vision, the beginning was not a single point, but a blur, a quantum haze from which space and time themselves emerged. The deeper scientists peered, the stranger the picture became. At the threshold of origin, relativity and quantum mechanics stood opposed, each offering pieces of truth but refusing to merge. One demanded the certainty of geometry, the other whispered of probability and uncertainty. Together, they suggested that the beginning was not a moment to be seen, but a paradox to be wrestled with. A universe could erupt into existence, yet the question of from what dissolved into abstraction. Time itself might have been born in that instant, leaving no before to be spoken of. For many, this was unsettling. The precision of COBE, WMAP, and Planck had seemed to push science closer to unveiling a first instant, a moment when existence itself lit its first spark. But at the boundary, clarity dissolved into fog. What had felt like answers gave way to deeper riddles. The cosmic microwave background, mapped in dazzling precision, confirmed that there was a beginning. Yet what that beginning meant, whether it was a singularity, a quantum fluctuation, or something stranger still, remained shrouded in mystery. It was here that cosmology entered its most haunting phase, where data met philosophy and where science itself brushed against the limits of comprehension. Humanity had seen the blueprint of creation in the faint glow of ancient light, but beyond that glow lay silence, paradox, and the unknown. The universe had confessed it had a birth. What it refused to say was why. The Planck satellite, launched in 2009, delivered the most detailed map of the early universe humanity had ever seen. Its detectors, cooled to near absolute zero, stared into the faint microwave sky with such sensitivity that it could detect variations in temperature of a few millionths of a degree. The result was a cosmic portrait that revealed not only the age of the universe with unprecedented ACC, URACY 13.8 billion years, but also its very composition. Planck confirmed that ordinary matter, the atoms that build stars, planets, and human life, made up less than 5% of all that exists. Dark matter accounted for roughly a quarter, and the rest, nearly 70%, was something even more elusive. Dark energy, a force driving the accelerating expansion of space. The afterglow of creation had spoken with precision, yet it spoke of ingredients that remained mysterious, whispering that most of the universe is built from what cannot be seen. These discoveries reshaped cosmology into a science both exquisitely exact and profoundly humbling. For while the CMB told of smoothness, it also revealed tiny anomalies, regions where the universe seemed slightly too aligned, patterns that could not be explained easily by inflation. One of these became known as the cold spot, a vast patch of sky unusually colder than expected, stretching across hundreds of millions of light years. Some proposed it was merely a statistical fluke, the chance arrangement of primordial ripples. Others speculated it might be evidence of something far stranger, a scar from a collision with another universe, a trace of realities beyond our own. Such interpretations remained unproven, yet they revealed how quickly the frontier of science can slip into the language of the surreal at the same time. The philosophical unease deepened. The more precisely cosmologists measured the universe's birth, the less clear its meaning became. Inflation solved many problems, but it came with consequences. If space could expand faster than light once, perhaps it could do so endlessly. Inflation might not be a single event, but an eternal process, spawning bubble universes beyond number, each with its own laws of physics. In this vision, our cosmos was not the beginning of all things, but one branch in an infinite cosmic tree, one spark among countless others. The Big Bang, long imagined as a singular beginning, might itself be only a local chapter in a story without end. Here, relativity and quantum mechanics clashed most vividly. Relativity described the grand sweep of space-time, while quantum mechanics insisted on the jitter of uncertainty at its smallest scales. In seeking to unite them, scientists pursued quantum gravity, a theory of beginnings that might reconcile singularities with probabilities. Loop quantum cosmology suggested that the Big Bang was not a beginning, but a bounce, a rebound from a prior universe that had collapsed under its own weight. String theory, with its hidden dimensions and vibrating filaments, offered yet another vision where the universe could emerge from the collision of higher dimensional membranes. None of these ideas were proven, yet all carried the same haunting implication. The moment once thought to be the birth of everything might instead be a veil, behind which lies another reality. For human imagination, this was both exhilarating and disquieting. The desire for a first spark, a single origin, runs deep in human culture and thought. To discover that the cosmos may not have begun at all, that it may instead cycle endlessly or branch infinitely, was to confront a truth both liberating and unsettling. It meant that existence might have no ultimate beginning, only layers upon layers of unfolding. The Big Bang, then, was not the answer, but the threshold, the edge of light before mystery resumes. In the silence between data points, in the unmeasured gaps of the cosmic map, lingered the most haunting paradox of all. Science had captured the earliest fossil of time, yet in doing so had unveiled the depth of what remains unknown. The afterglow carried the memory of the universe's first breath, but beyond it stretched a horizon where language falters, where the very concept of beginning dissolves into paradox. The closer humanity drew to origins, the less solid the ground beneath its feet became, until even time itself seemed uncertain, fragile, and perhaps illusory. At the frontier of modern cosmology, the question of beginnings dissolves into something stranger than any myth. Physics, when pressed to its limits, resists the notion of a singular first instant. Time, as described by Einstein's relativity, stretches and bends with the fabric of space, yet as equations are wound backward toward the earliest moments, they collapse into infinities, singularities where density becomes immeasurable, where the laws themselves shatter. To many, this breakdown signals not a true beginning, but a clue that the language of physics must change. Infinity is the mind's red warning light, a signal that the framework has reached beyond its domain. The universe, then, may not have been born from nothingness, but from a state our current understanding has no words to describe. Stephen Hawking, with James Hartle, sought to replace the riddle of a singular beginning with a vision drawn from geometry itself. Their no-boundary proposal suggested that time may be finite, yet unbounded, like the surface of a sphere. A traveler moving across the earth eventually circles back to their starting point without ever encountering an edge. So too, they argued, could the universe exist without a sharp beginning. In this view, the earliest moments of the cosmos fade smoothly into a realm where the distinction between time and space loses meaning. The singularity is softened. The question of before ceases to exist. It is not that the universe emerged from nothing, but that the idea of before the beginning was always a misstep of language. Other visions embrace the rhythm of cycles. In loop quantum cosmology, equations suggest the Big Bang may not have been a birth but a bounce. A universe contracting into crushing density might rebound, giving rise to a new expansion. In such models, every Big Bang carries the echo of a big crunch before it, and the cosmos becomes an endless heartbeat. Collapse, rebound, expansion, collapse again. The ashes of one universe seed the fire of another, in an eternal cycle that strips the word beginning of finality. To think in cycles is to confront a deeper form of infinity, not an abstract mathematical divergence, but a lived eternity where existence continually remakes itself. The multiverse stretches this vision further still. If inflation can spark entire universes, then ours may be one among countless others, each with its own laws and histories. In such a landscape, the Big Bang becomes a local phenomenon, not the dawn of all reality, but the opening of one region of an infinite sea. What appears as a beginning may only be a transition, a bubble forming in the quantum foam of the greater whole. This possibility is impossible to prove and perhaps forever beyond observation, but it lingers like an uninvited shadow over cosmology. It hints that the most profound truths may lie forever beyond the horizon of what a single universe can reveal. Mathematics itself resists the notion of a first instant. Equations bend and warp as they near zero, as if protesting the demand for a beginning. The infinities that emerge at singularities are not just technical inconveniences, they are signs that reality may not permit. The crisp boundary lines the human mind longs for. Instead, every attempt to corner the universe into a single starting point seems to reveal a deeper mystery, a retreating edge that moves further as knowledge advances. The horizon of beginnings always recedes, like a mirage in the desert of time. For human thought, the emotional weight of this is immense. To stand at the edge of cosmic understanding is to face a paradox. Every step forward sharpens the picture of the universe, yet the origin itself slips further from grasp. It is as though time itself were a horizon, glowing faintly in the distance, yet always withdrawing when approached. The desire for a first spark remains, but the cosmos whispers a more unsettling truth, that beginnings may be illusions, that the fabric of reality is not a story with a first page, but a circle, a sea, or a vast branching forest without root. To search for the ultimate origin is to chase the retreating line where knowledge meets mystery, a pursuit that may never end, yet forever defines the human quest to understand. At the limits of observation and theory, physics becomes less a map of certainties and more a meditation on the boundaries of knowledge. Stephen Hawking's no-boundary proposal was not merely a mathematical exercise. It was an attempt to reframe existence itself. Instead of a hard origin point where all laws collapse, Hawking and Hartle imagined a smooth geometry in which time slowly emerges from a timeless state, like dawn from a long night. In their equations, the universe near its earliest moments was not bound by the ordinary flow of time at all. It was more like space, a dimension that curved and closed, finite, yet without an edge. Just as one can walk endlessly across Earth without falling off a boundary, so too could the universe exist without a singular starting instant. The language of beginnings, in this light, loses meaning. Asking what came before the Big Bang becomes as meaningless as asking what lies north of the North Pole. This vision challenged the most ancient human instinct, the craving for a first cause. Every culture, every myth, every philosophy has sought a primal spark. Yet physics seemed to whisper something different, that perhaps there was no single spark at all, only a seamless unfolding, a geometry where questions of before and after dissolve. This was both liberating and unsettling. To live in such a universe meant to accept that origins may not exist as stories, but as structures too alien for narrative. Still, not all theories erased the notion of a dramatic birth. Some, guided by the mathematics of quantum gravity, proposed that the Big Bang itself was not a beginning but a transition. In loop quantum cosmology, the relentless collapse of a dying universe does not end in a singularity, but in a quantum rebound, a bounce from contraction into expansion. The equation suggests that space cannot be crushed into infinite density. Instead, the geometry of space-time resists, rebounding like a spring. What humans call the Big Bang may therefore be the aftershock of a prior collapse. In this vision, universes do not begin or end, they breathe. They inhale and exhale across eternities, each cycle burning away its structures only to rise again, remade from its own ruins. Such a cyclical cosmos carries profound philosophical weight. It dissolves the need for a unique beginning, but at the cost of confronting infinity in its most haunting form, not a cold, mathematical abstraction, but an eternal procession of worlds. To imagine such cycles is to imagine a universe without final answers, where every ending folds seamlessly into another dawn. Humanity, in this perspective, lives not in the first creation, but in one verse of an endless epic written by the cosmos itself. And then there is the multiverse, a possibility that stretches the imagination beyond any single story of time. According to inflationary cosmology, the same physics that smoothed and stretched our universe may continue eternally, spawning countless bubble universes within an inflating sea. Each bubble begins with its own Big Bang, each with its own laws of nature. Some may collapse in moments, others may expand into infinite spacetimes. Our cosmos, with its galaxies and its life, may be one such bubble, fragile and transient, surrounded by an unseeable infinity. In this framework, the beginning of our universe was not the beginning of reality, but a local flare within a boundless ocean of creation. This vision unsettles as much as it inspires. It denies the hope of a single origin, for even if one traces our own Big Bang back to its source, the larger inflating sea lies beyond, and perhaps beyond that still more levels of reality. Every attempt to pin down a first cause ends not in closure but in expansion. The horizon recedes further, and the search for beginnings dissolves into a search for structure in an endless hierarchy of worlds. For some, this represents the ultimate beauty, a reality forever larger than imagination. For others, it is a cosmic vertigo, stripping away the hope of a final answer. Mathematics itself bears witness to this paradox. When equations are driven toward the singularity of the Big Bang, infinities erupt, densities without bound, curvatures beyond measure. These infinities are not merely technical problems, they are warnings, markers that the conceptual tools of physics have reached their limit. They stand like ancient guardians at the edge of knowledge, signaling that what lies beyond requires a new language, one not yet invented. Every attempt to tame the singularity through quantum gravity, through string theory, through speculative mathematics, is a step toward such a language. Yet the horizon continues to shift. Like a mirage in the desert, the beginning appears, always just ahead, visible in outline but dissolving when approached. The human response to this is deeply emotional. The mind yearns for certainty, for a first chapter that gives coherence to the story of existence. The idea of a singular beginning feels fragile yet comprehensible, a point from which everything flows. But the deeper physics delves, the more that simplicity evaporates. Instead, the cosmos seems to insist that reality is not a line with a starting point, but a circle, a cycle, or an infinite branching tree. To live in such a universe is to accept that the origin is not an event, but an eternal horizon, one that can be approached endlessly but never touched. It is here, at this frontier, that science becomes philosophy. The search for the first instant turns into a meditation on the nature of time itself. The universe may not have a beginning in the human sense, yet it has structure, rhythm, and law. It may not offer a spark to satisfy myth, but it offers patterns that echo eternity. In the interplay of cosmology and quantum theory, humans glimpse not an origin but a horizon, one that defines the quest as much as the answer. The journey to understand beginnings becomes, in truth, a journey to understand why beginnings matter. At all, in the imagination of science, there lies a region so remote that even the most powerful equations fracture under its weight. This frontier is called the Planck epoch, the first sliver of existence, less than a trillionth of a second after what is called the beginning. Here, gravity is not the smooth, curving fabric described by Einstein, but a storm of fluctuations at scales smaller than atoms. Space itself would boil with quantum foam, time would lose all coherence, and the very categories of before and after would dissolve into a haze of possibility. It is the most extreme horizon in physics, a place where the known laws of reality collapse into silence. Scientists know this epoch, not because they can describe it, but because they cannot. The very failure of relativity, when pushed to such extremes, announces the need for a deeper theory. String theory was one of the boldest attempts to fill that void. It suggests that the universe is not built from indivisible particles, but from tiny vibrating strings whose frequencies determine the forms of matter and force. If true, then reality is not an assembly of points but a symphony of vibrations, an eternal music that has no first note. Time, in this vision, does not begin. It resonates, weaving patterns upon patterns, as though the universe were a timeless score always unfolding. Others turn to loop quantum cosmology, a radical approach born from the attempt to quantize space itself. In this framework, space-time is not continuous but woven from discrete loops, tiny quanta of geometry. When a universe collapses toward a singularity, these loops resist infinite compression, forcing a rebound. Instead of a catastrophic beginning, there is a bounce, a passage from contraction to expansion. The Big Bang, in this light, was not a birth but a transition, one heartbeat in an infinite cycle of cosmic breaths. Such a universe has no singular origin, only rhythms without end. The holographic principle deepens the mystery further. It suggests that the three-dimensional universe may not be fundamental at all, but a projection from a deeper two-dimensional surface, a kind of cosmic hologram. If true, then time itself may not be a primary ingredient of existence, but a construct emerging from relationships written on a hidden boundary. In this vision, beginnings dissolve entirely, for a projection cannot be said to start in the same way a physical object does. The birth of the cosmos might be less like the ignition of a fire and more like the turning of a page in a book that has always existed. Yet every such vision collides with a haunting paradox, entropy. The second law of thermodynamics dictates that disorder grows with time, that energy spreads, that systems decay. In a universe without a beginning, how could entropy not have already reached its maximum long ago? How can order still exist, galaxies still shine, life still emerge, if infinite ages have already passed? This puzzle unsettles even the boldest cosmologies. It whispers that there is something still missing in our understanding, something hidden in the nature of time itself, for perhaps time is not fundamental at all. Increasingly, physicists and philosophers alike entertain the possibility that time is an illusion, not a river flowing from a source to a sea, but a pattern woven by deeper, timeless laws. In such a picture, what is called the beginning may be no different from any other moment, a point within an eternal whole that has no first or last. The arrow of time may arise only as an emergent property, a trick of entropy, a perspective bound to beings who measure change but never touch the timeless fabric beneath. If so, then all talk of origins may be a projection of human imagination onto a universe that never needed them. The Planck epoch, the bounce, the hologram, the entropy paradox, all may be signposts pointing not toward a birth, but toward a revelation that beginnings themselves are illusions, horizons that vanish as one approaches, mirages on the edge of comprehension. In such a cosmos, existence does not start, it simply is. Timeless, seamless, endless a mystery without a first instant, unfolding like a story that was never written, but always already present. The Planck epoch remains the ultimate riddle at the foundation of modern cosmology. Less than 10 seconds after the supposed birth of the cosmos, the known forces of nature merge into a storm of incomprehensible unity. In this infinitesimal slice of time, the distinction between gravity and quantum mechanics collapses. The universe was not yet a canvas upon which galaxies could someday be painted, nor even the faint glow of plasma that later filled the void. Instead, it was a sea of quantum foam, a chaos of fluctuations so violent that the very concept of geometry lost its meaning. Distances could not be measured, durations could not be defined, because the stage on which such measurements rely, space-time itself, was not yet stable. In that storm, the familiar rules of relativity failed, overwhelmed by the surging unpredictability of quantum mechanics. It is here, in this darkness, that science reaches a wall it cannot yet breach. String theory emerged as a daring attempt to illuminate this hidden epoch. It proposed that what we call particles, electrons, quarks, photons, are not points but threads of energy, one-dimensional filaments vibrating at precise frequencies. Each vibration gives rise to a property, like mass or charge, and together they form the great orchestra of existence. If this picture is true, then even in the Planck epoch, there was never a singular explosion out of nothing. Instead, there was a field of eternal resonance, a music without a beginning. Strings vibrated not within time, but in a deeper layer from which time itself would eventually arise. This vision carries with it profound implications. If the foundation of reality is a timeless song, then the so-called Big Bang may not have been the start of the symphony, but only the point where the melody became audible. Yet string theory also opens doors that strain human imagination. Its equations suggest the existence of not one universe, but a vast landscape of possible universes, each with its own laws, its own constants, its own histories. Our cosmos may be one bubble among countless others, its apparent beginning, nothing more than a transition from a pre-existing sea of possibilities. In such a multiverse, origins lose meaning because beginnings are everywhere and nowhere. Every spark of existence could be the echo of another, and behind them all lies an infinite tapestry of potential worlds that may never be observed, yet still shape the contours of reality. Parallel to this loop, quantum cosmology offered another kind of answer. By treating space-time itself as quantized, woven from discrete loops of area and volume, it suggests that a singularity is never reached. Instead, as the cosmos contracts under its own gravity, space reaches a minimum size, where quantum repulsion halts collapse. Then a bounce occurs, and expansion begins anew. In this view, the Big Bang is not creation ex nihilo, but a rebound, the latest cycle in an eternal dance of contractions and expansions. The universe does not emerge from nothing, but from its own shadow, collapsing and reawakening like a cosmic heartbeat. This model hints at a reality where death and birth are illusions of scale, and the cosmos itself is as ageless as the rhythm that sustains it. The holographic principle casts yet another perspective. According to this idea, the three-dimensional universe we perceive might be a projection, like an image cast from a two-dimensional surface. The information of the cosmos is stored not in the volume of space, but on its boundaries, just as a hologram encodes depth within a flat sheet. If this is true, then time itself is part of the projection, not a fundamental ingredient of reality. A beginning, in this case, is no more meaningful than asking when the holographic film itself was born. The deeper reality contains all moments, at once timelessly encoded, and what we perceive as flow and change is a manifestation of a higher order that never begins and never ends. But lurking beneath every attempt to reimagine the first instant lies the stubborn law of entropy. The second law of thermodynamics demands that disorder increases with time, that energy diffuses, that complexity eventually collapses into heat and uniformity. If the universe has no beginning, if cycles extend infinitely into the past, why? Has entropy not already reached its maximum? Why do stars still shine, galaxies still form, and life still emerge in a cosmos that should long ago have burned out into equilibrium? This paradox gnaws at the foundations of eternal models. It suggests that there is something deeply hidden in the relationship between entropy and time, some principle not yet revealed. Perhaps entropy itself, like time, is emergent, a rule that applies only within the unfolding of experience, but not to the deeper layers where reality is stitched together. And so, the question arises, what if time itself is not real? Increasingly, theories of quantum gravity, as well as interpretations of relativity, point toward the possibility that time is not fundamental but emergent. It may arise from correlations between events, from the entanglement of states, from the way systems evolve relative to one another, not from a universal clock. In this sense, the universe does not flow from past to future. Instead, all of existence may be laid out in a timeless structure, where beginnings and endings are illusions created by limited perspective. The human mind, bound to memory and expectation, experiences time as a river, but the river may be no more than a reflection on a still and boundless sea. Standing at this edge of science is like standing before a horizon that forever recedes as one approaches. The Planck epoch, the bounce, the hologram, the entropy paradox, each is a lens through which the universe refracts its mystery, never yielding fully to human comprehension. Perhaps there was never a first spark. Perhaps the universe has always been timeless and unbounded, its story woven into a fabric that requires no origin. Or perhaps the concept of origin itself is flawed, a shadow cast by beings who measure beginnings because they themselves are finite. Beyond the horizon, only silence remains, a silence that may hold the truest answer of all, that the cosmos is not a tale that started, but an eternal presence without beginning or end. From the prevailing view of modern cosmology emerges a story both elegant and incomplete, a narrative that has dominated scientific thought for nearly a century. It begins not with silence, but with a surge, a universe compacted into a state of unimaginable density and heat, expanding outward in an instant that defies comprehension. This event, known as the Big Bang, remains the cornerstone of mainstream physics, yet even this phrase, suggestive of an explosion into emptiness, fails to capture the subtlety of what occurred. Space itself expanded, carrying with it all energy, all matter, all future structure. There was no exterior into which it burst, only the sudden stretching of the very fabric that would come to cradle galaxies, stars, and worlds to account for. The smoothness of the cosmos, for its vast uniformity despite being born from such violent beginnings. Physicists proposed a remarkable addition, cosmic inflation. In the first fractions of a second, the universe is believed to have ballooned exponentially, swelling far faster than the speed of light, ironing out irregularities, erasing curvature, and stretching quantum ripples across cosmic scales. Those ripples, microscopic in origin, became the seeds of galaxies. Tiny fluctuations in the quantum vacuum were frozen into the fabric of space during inflation, later amplified by gravity into the colossal web of structure that now spans billions of light years. Every star, every planet, every living being may trace its lineage to those primordial whispers of uncertainty. And so the mainstream story stands, a tapestry woven of bold theories and silent boundaries. It tells of inflationary birth, quantum seeds of galaxies, black holes that evaporate, entropy's unstoppable arrow, and possible fates of death or rebirth. Yet even within this carefully built framework, questions linger. Why did the universe begin in such a low entropy state? What set inflation in motion, and why did it end? Is dark energy constant, or is it a shadow of deeper physics? Still unknown. Each answer spawns new mysteries. Each theory extends the horizon of ignorance. The mainstream narrative, for all its triumphs, is less a final truth than a lantern held in a cavern, illuminating part of the vast darkness while leaving most still concealed. The story continues, suspended between clarity and silence, between what can be known and what forever escapes. From the foundation of mainstream cosmology, the narrative extends into realms more speculative, where physics brushes against philosophy and the border between science and imagination begins to blur. Here, the theories do not simply describe a universe, but suggest a multiverse, a reality vaster than the human mind can contain. One such vision emerges from the theory of eternal inflation. If the inflationary expansion that shaped the early universe is not a singular event but a perpetual process, then our cosmos may be only one bubble within an endless froth. Each bubble universe would possess its own physical constants, its own laws of nature, and its own history. Some may expand like ours, filled with galaxies and stars. Others may collapse almost as soon as they appear. From this perspective, the Big Bang is not a unique origin but a local beginning, one among countless others. The landscape becomes infinite, with universes budding into existence without end, like seeds scattered on a boundless ocean. If this is true, then the story of existence is not about a singular creation, but about an eternal unfolding of worlds, each beyond the reach of the others, forever hidden yet hauntingly suggested by the mathematics of inflation. Roger Penrose offers a different vision, one that reshapes the very boundaries of time. In his conformal cyclic cosmology, the heat-death of one universe becomes indistinguishable from the birth of another. When a cosmos has expanded so far that all particles lose their identity and no clocks can measure the passing of time, the end state mirrors the beginning. In this view, universes follow one another in an infinite chain of cycles, each eon giving way to the next. Evidence for this radical idea has been sought in subtle imprints on the cosmic microwave background, faint circular patterns that might whisper of events from a universe before our own. Whether or not these imprints are real, the vision is profound. Time does not stretch from a singular beginning toward a single end, but loops endlessly, like waves rising and falling upon a cosmic shore. The ekpyrotic models draw inspiration from dimensions beyond perception. According to these theories, our universe was born not from a singularity, but from the collision of higher dimensional membranes, brains drifting in a greater space. The violent impact released energy, igniting a cosmos of matter, radiation, and expansion. Unlike the Big Bang singularity, this scenario allows for a before, a history of motion in a hidden higher dimensional realm. In some versions, these brain collisions occur repeatedly, each strike producing a new universe. The cosmos becomes not a singular event, but a rhythm of impacts echoing through an invisible dimension, with each collision seeding a new reality. Though speculative, the mathematics of string theory permits such constructs, suggesting that what we see may be but the shadow of deeper, unseen geometries. Other theories question whether time itself is fundamental. If time is emergent rather than primary, then the search for a beginning may be misguided. Time may arise only when particles interact, or when entropy unfolds. Without change, without observers, without distinctions between states, there may be no time at all. In this framework, asking what came before the universe becomes meaningless, because before implies a timeline that did not yet exist. The universe may simply be timeless, eternal, with time as a mirage that emerges. Within it, this radical possibility challenges not only physics, but human intuition, for it suggests that beginnings and endings may be illusions, and that the river of time we experience is a local phenomenon, not a universal truth. Even black holes, those enigmatic graves of stars, have been reimagined as potential wombs of universes. If the singularity within a black hole does not mark a final collapse, but a bridge to another domain, then every black hole may contain its own cosmos, sealed off from ours. In this scenario, universes reproduce each black hole becoming the seed of a new expansion. Our own Big Bang could have been the birth throes of such a process, emerging from the depths of a collapsing star in another universe. This perspective recasts the cosmos not as a lone creation, but as an ongoing tree of universes, each sprouting from the death of stars within another. The familiar cycle of birth and death extends from biology to cosmology, from the smallest cells to the largest scales of reality. At the farthest edge lies an idea not from physics alone, but from the merging of science with philosophy and technology. The simulation hypothesis. According to this vision, the universe is not physical in the ultimate sense, but computational. The laws of physics are the rules of a code, the constants of nature parameters chosen by an unseen architect. If this were true, then beginnings are not cosmic at all, but digital moments when a program is initiated. The Big Bang would not be an explosion of matter and energy, but the instant when code began to run. Though untestable with current knowledge, the notion highlights the strangeness of our reality, that the order of the universe is written in mathematical form, that nature itself behaves like information. Whether or not it is literal, the simulation hypothesis underscores the uncanny correspondence between physics and computation, between matter and mathematics. Together, these speculative theories form a kaleidoscope of possibilities. Eternal inflation points toward an infinite multiverse. Penrose envisions endless cycles. The ekpyrotic model reveals hidden dimensions. Emergent time dissolves beginnings. Black holes give birth to universes, and the simulation hypothesis casts reality as code. None of these ideas have been proven, and many may remain forever beyond confirmation. Yet they expand the horizon of thought, forcing recognition that the universe may be stranger, deeper, and more elusive than any single theory can contain. They remind that science is not only a catalogue of what is known, but a window into what might be a dialogue with the unknown, conducted in the language of imagination and mathematics. Eternal inflation is perhaps the most dizzying of these speculative visions, because it forces the imagination to confront infinity not as a poetic metaphor, but as a physical inevitability. In this picture, inflation, the runaway expansion that once drove our infant universe apart faster than the speed of light, is not a brief chapter, but an ongoing engine, eternally bubbling, eternally spawning. Local regions where inflation slows give rise to universes like ours, while elsewhere it rages on, endlessly birthing new domains of space-time. The consequence is a multiverse so vast that every possible history, every variation of physics, might unfold somewhere. In one universe, galaxies cluster more tightly. In another, stars never ignite. Some universes may contain beings who look up at alien skies and ask the same questions that echo through human thought. Others may remain sterile, barren fields of possibility where complexity never takes root. The mathematics of eternal inflation does not merely permit this, it almost demands it. Yet the scale of such a reality presents an unsettling paradox. If there are infinite universes, then ours is not special. Every outcome, no matter how improbable, must occur. The cosmos becomes a library without end, filled with books that tell every story, real or imagined, repeated endlessly across the shelves of infinity. Against this backdrop, Penrose's conformal cyclic cosmology takes on a different kind of elegance, where eternal inflation scatters universes into endless diversity. Penrose envisions a single universe that reincarnates across infinite cycles. Each eon stretches so far into the future that all structures dissolve, all black holes evaporate, and all mass fades into pure radiation. When nothing remains that can measure duration or distinguish change, time itself loses meaning. The infinite cold and silence of heat death then becomes indistinguishable from the initial conditions of a new Big Bang. In this sense, the end of one universe is already the beginning of another, stitched together by the mathematics of conformal geometry. Penrose has even suggested that faint traces of previous eons may be visible in the cosmic microwave background, concentric rings, left by the decay of supermassive black holes long before our universe was born. The evidence remains disputed, but the idea itself reshapes the notion of beginnings. Instead of a singular creation, the cosmos becomes a phoenix, forever rising from its own ashes, carrying whispers of its past into each new cycle. The model offers another vision of rebirth, but its stage is larger still. Instead of cycles driven by entropy and geometry, it imagines vast cosmic membranes existing in dimensions beyond our perception. Our universe is but one such brain, floating in a higher dimensional bulk. When these brains collide, the energy released manifests as a Big Bang, seeding matter, light, and time itself. Unlike the singularity of classical cosmology, this framework suggests that before our universe, there was motion, history, and interaction, a deeper story hidden beyond the veil of the dimensions we can see. Some versions propose that such collisions repeat indefinitely, universes being forged again and again in the rhythm of higher dimensional impacts. If true, then the Big Bang was not the beginning, but a violent punctuation mark in a grander narrative, like a spark struck from the collision of unseen titans drifting through a space beyond comprehension. More radical still is the notion that time itself is not fundamental. In many quantum gravity approaches, time does not exist at the deepest level of reality. Instead, it emerges only when states of matter and energy are compared, when entropy increases, when differences unfold. In this picture, the universe is not a story told from beginning to end, but a timeless whole, with time as an illusion that arises within it. What we call the flow of time may be nothing more than the unfolding of correlations, the blossoming of order into disorder. If time is emergent, then the very question of a beginning becomes misdirected. A beginning assumes a timeline to measure against, but if time is not primary, then perhaps the universe simply is eternal, changeless, beyond the categories of past and future. This possibility is profoundly unsettling, for it undercuts the deepest intuition of human experience, that time flows, that lives unfold, that beginnings and endings mark existence. Yet it may be that time is not the river we imagine, but a surface ripple on a deeper ocean, a mirage that flickers into being only under certain conditions. Black holes, those cosmic abysses where gravity overpowers all escape, add another layer of speculation to the mystery of beginnings. If singularities at their cores do not represent an end but a bridge, then every black hole could be a portal to another universe. In such a model, the collapse of a massive star does not terminate in finality, but in creation, with the singularity expanding into a new cosmos on the other side. Our own universe may be the offspring of such a collapse in another reality. Its Big Bang, the mirror image of a black hole's implosion elsewhere. This concept transforms black holes from tombs into wombs, each one a seed containing the potential for an entirely new universe. It extends the principle of cycles into an organic metaphor. Just as stars die to give birth to new generations of stars, so too might universes be born from the death of stars within parent universes. The cosmos becomes not a solitary structure, but a vast genealogical tree, with branches and roots intertwining across realities. At the farthest speculative horizon lies the simulation hypothesis, which suggests that all of reality is not physical at its core, but computational. The laws of physics become the rules of a program, the constants of nature parameters chosen by some deeper intelligence. In such a vision, the Big Bang is not a cosmic explosion, but the moment when a system was initialized, when code began to run. The perception of time, the growth of entropy, even the birth and death of stars could all be the unfolding of an algorithm. Though this idea is far from empirical science, it underscores a strange truth, that the universe is already written. In the language of mathematics, that matter behaves like information, that the structure of reality can be read as computation, whether literal or metaphorical. The hypothesis resonates because it speaks to the uncanny fit between mathematics and the physical world. It asks whether the reason the universe obeys mathematical laws is because, at its core, it is mathematics. These theories, eternal inflation, cyclic cosmology, brain collisions, emergent time, black hole universes, and simulations, do not converge on a single answer. Instead, they illuminate the profound uncertainty at the heart of cosmology. The origin of the universe remains not a solved equation, but a horizon, a boundary where imagination and evidence meet. Each theory extends human vision a little farther, opening possibilities that challenge the very fabric of meaning, what it means for something to begin, to end, to exist. They remind that the mystery of the universe is not diminished by knowledge, but deepened. Each new theory a doorway into an even greater unknown. The quest to understand beginnings has now shifted from the realm of thought experiments and philosophical speculation to the relentless precision of modern instruments, observatorius, and machines built on a planetary scale. Today, the search for cosmic origins unfolds in steel and glass, in silicon circuits and superconducting magnets, in mirrors polished to near perfection and detectors cooled to temperatures colder than the void of space itself. Humanity has taken its longing to know how everything began and placed it into the design of machines that extend its senses beyond imagination. These efforts, scattered across the globe and orbiting high above the Earth, form a mosaic of attempts to reach backward, toward a time when the universe itself was still gathering its breath. The James Webb Space Telescope now hovers far beyond the obscuring glow of Earth's atmosphere, its golden mirrors tilted like the eyes of a patient oracle gazing across cosmic time. With infrared vision, it pierces through dust and distance, revealing galaxies so ancient that their light has been traveling toward us for over 13 billion years. In those faint smudges of red-shifted glow lie clues to the moment of first light, when the darkness that followed the Big Bang was broken by the birth of stars. And yet, the deeper Webb peers, the stranger the story becomes. Galaxies appear earlier and more developed than many models had predicted. Structures that should have taken hundreds of millions of years to form seem to have emerged almost immediately. Instead of confirming neat theories, Webb delivers tension, paradox, and the unsettling hint that the narrative of cosmic dawn may be more complicated than imagined. Each photon it captures whispers of a universe that may not have unfolded according to the timelines once thought secure. On the Earth below, particle accelerators, like the Large Hadron Collider, mimic creation on a smaller scale, colliding protons at near light speeds to briefly recreate the energies of the primordial fireball. Within these collisions, for fractions of a second, matter exists as it did in the earliest instance, after the Big Bang, a searing plasma of quarks and gluons unbound. from the protons and neutrons they now inhabit. Detectors encircled the collision points, recording showers of exotic particles as if each event were a miniature rehearsal of cosmic origin. These machines cannot replicate the whole of creation, but they can reveal the rules by which matter and energy behaved when time itself was young. The discovery of the Higgs boson in 2012 confirmed one piece of this puzzle. The field that gives particles mass is real, but the very same discovery sharpened the mystery, hinting at instability in the fabric of the universe, a false vacuum that could, in principle, collapse into a deeper state of reality. In probing the smallest scales, humanity finds echoes of the largest questions. Debates rage over whether the cosmic microwave background, long hailed as the most convincing relic of the Big Bang, is truly the definitive evidence of a beginning. This faint bath of radiation, stretched into microwaves by the universe's expansion, has been studied in exquisite detail by satellites such as COBE, WMAP, and Planck. Its slight fluctuations in temperature, no more than a few parts in 100,000, have mapped the seeds of cosmic structure. Yet some physicists ask whether these patterns could admit other interpretations. Could they be the afterimage of a universe before ours, as Penrose suggested? Could they contain scars of higher dimensional collisions, or artifacts of unknown physics that predated the fireball? The CMB has become both cornerstone and battleground, a canvas upon which the deepest cosmological theories are projected. Each map of its fluctuations is less an answer than a mirror, reflecting competing visions of where the story truly begins. Meanwhile, astronomers search for gravitational waves that might carry imprints from before the Big Bang itself. Unlike light, which can only travel through the universe after it became transparent, gravitational waves ripple through space-time itself. If the universe once passed through phases of violent expansion, contraction, or collision, those tremors could still echo today. Sensitive detectors like LIGO and Virgo have already heard the whispers of merging black holes. But to detect primordial gravitational waves requires instruments even more delicate, space-based observatories like the planned LISA mission, capable of listening to the universe in tones deeper and older than anything light can reveal. To capture such a signal would be to hear the heartbeat of creation itself, vibrations imprinted upon the cosmos before stars or atoms existed. Supercomputers, with their labyrinths of processors, carry on a parallel mission to simulate entire universes from first principles. Within their digital confines, physicists model the dynamics of particles, fields, and expansion, seeking ways to avoid the singularity where equations break down. Some simulations suggest that quantum gravity might smooth the supposed beginning into a bounce, where contraction leads not to an end but to a renewal. Others explore universes with no clear origin, where fluctuations in quantum fields generate space-time without a single moment of birth. Each run of code plays out a cosmos in miniature, its galaxies and voids growing under artificial gravity, its histories unfolding within electronic memory. These digital universes are not the real one, but they reveal possibilities, a rehearsal of creation where theory confronts the test of coherence. Yet even as these monumental efforts progress, the tension remains. Every answer gives rise to sharper questions. Webb uncovers galaxies too early. Accelerators find instabilities in the vacuum. Background radiation admits multiple interpretations, and simulations multiply rather than resolve the possibilities. The universe reveals itself not as a solved puzzle, but as a horizon receding with every step toward it. The closer one comes to the beginning, the more the beginning dissolves into paradox. Perhaps this is the ultimate lesson, that the search for origins is not about reaching a final answer, but about deepening the intimacy between mind and cosmos, between human curiosity and the mystery it seeks. The machinery of science does not close the question of creation. It expands it, transforming each discovery into a deeper invitation to wonder. Each advance in observation and experimentation carries with it a weight of both revelation and unease. The James Webb Space Telescope, suspended in the cold darkness beyond Earth, does not merely collect photons. It deciphers whispers from the dawn of time, tracing the first clusters of stars and galaxies as if reading the universe's earliest diary. Each faint, reddened galaxy, appearing so young and already structured, defies expectations, challenging assumptions about the pace and mechanics of cosmic formation. The telescope's instruments tease out signatures of chemical composition, star formation rates, and the assembly of massive structures, yet every discovery raises further questions. How could galaxies form so rapidly in a universe still in its infancy? Was there a hidden acceleration, a mechanism beyond the reach of standard cosmology? Webb's vision illuminates the deep past, but it also casts longer shadows, revealing that the narrative of beginnings may be far more intricate than previously imagined. A tapestry woven with both visible threads and invisible patterns still waiting to be understood. On Earth, particle accelerators continue the work of recreating primordial conditions, smashing protons together with energies so extreme they mimic the searing heat and density of the early cosmos. The Large Hadron Collider and its detectors are monuments to human curiosity. They're instruments designed to capture the ephemeral traces of particles that exist only in these extreme conditions. Every collision produces a cascade of quarks, gluons, and exotic resonances, ephemeral manifestations of the universe in its first trillionths of a second. In these bursts of energy, physicists glimpse the symmetry and structure of the laws governing matter, the scaffolding upon which all else is built. Yet the results often deepen the mystery. The Higgs boson, while confirming the mechanism that gives mass, hints at a vacuum that may be metastable, suggesting that the universe could, in principle, transition to a deeper state. Here, in the controlled chaos of the collider, creation is both witnessed and questioned, a reminder that even in replicating the past, certainty remains elusive. The cosmic microwave background remains both a guide and an enigma, detected as a faint, uniform glow pervading all of space. It was once hailed as the definitive fingerprint of a beginning. Yet, as our instruments probe its tiny fluctuations, with ever greater sensitivity, debates arise over their interpretation. Some see in these anisotropies a record of quantum fluctuations stretched by inflation. Others, inspired by Penrose, look for hints of events from universes that existed before our own concentric patterns that might be echoes of previous eons. Each new map, each refinement in data, adds nuance but no finality. The radiation that once seemed to confirm a singular moment of origin now reveals the possibility of deeper layers, histories that precede or lie outside the timeline we thought we understood. Gravitational waves offer yet another frontier. Unlike light, which emerges only after the universe became transparent, these ripples move through the very fabric of space-time. Instruments like LIGO and Virgo have already detected signals from colliding black holes and neutron stars, confirming predictions of general relativity. Yet physicists now dream of detecting waves that predate even the cosmic microwave background, disturbances imprinted by the earliest epochs, or perhaps by events that occurred in a pre-Big Bang phase. Space-based observatories, such as LISA, aim to listen to these whispers, to perceive the faint tremors of reality itself as it unfolded from the most extreme conditions. To detect them would be to hear the echo of creation, to witness a vibration that resonates not in light or matter, but in the structure of existence itself. Meanwhile, supercomputers model entire universes, constructing reality from equations, rather than matter. Within these simulations, singularities can be smoothed, time can be altered, and universes without classical beginnings can emerge. Researchers test scenarios in which the Big Bang is replaced by a quantum bounce, where contraction leads to expansion without ever passing through infinite density. They simulate multiverses, brain collisions, and emergent time, exploring the boundaries of what is mathematically consistent and physically plausible. These digital experiments are not reality itself, yet they allow scientists to play with the architecture of creation, to witness how different laws might produce different cosmic tapestries. Each run of code extends the mind's reach, probing possibilities that lie forever beyond direct observation. Even as these efforts advance, a profound tension persists. Every new observation, from Webb's ancient galaxies to the subatomic collisions of the LHC, both illuminates and destabilizes. The cosmic microwave background, gravitational waves, and simulations all offer pieces of a puzzle that continually shifts shape. Answers give rise to new questions, certainty dissolves into paradox, and the very idea of a singular beginning becomes increasingly fluid. Humanity's gaze, sharpened by technology, meets the universe not with finality but with awe, realizing that understanding may be less about reaching a beginning and more about tracing the interplay between knowledge and mystery. Each photon captured, each particle detected, each digital universe rendered, becomes a dialogue with the cosmos. A reminder that science does not close the question of origin, but deepens it, revealing that the search itself, the pursuit of comprehension across space and time, is part of the universe's story. In the quiet hum of observatories, in the frozen detectors of colliders, and in the algorithms of supercomputers, the universe seems to whisper its secrets while holding the ultimate answer just out of reach. Scientists continue to measure, simulate, and theorize, standing at the edge of what can be known, aware that the deeper the gaze, the more the mystery expands. In this pursuit, the human mind mirrors the cosmos itself, endlessly unfolding, ever searching, eternally reaching toward horizons that recede as they are approached. Each effort is both revelation and reflection, a testament to curiosity, to wonder, and to the unending dialogue between existence and comprehension. In contemplating a universe without beginning or end, the mind drifts into vast uncharted territory. Time, as once measured by sunrise and shadow, by tick of clocks and heartbeat, dissolves into a horizon with no edges. Humanity has long craved origins, the story of a first spark, the narrative of a cosmic birth, yet the possibility that such a story does not exist is both liberating and unnerving. A cosmos eternal in duration, endless in scope, resembles a book without a first page, without a final chapter. There is no starting point to anchor meaning, no final act to bring closure. The human impulse to understand, to sequence events into beginnings, middles, and endings, is confronted with a reality that that defies such framing. Yet within this boundless expanse, there is a strange beauty. Every moment is already a continuation. Every life a thread woven into an infinite tapestry, carrying significance precisely because it exists within an unending whole. The existential paradox becomes palpable. If the universe has no origin, then the stories of creation, of purpose assigned by beginnings, are narratives we impose upon it. And yet, our lives are necessarily framed by beginnings and endings. The first cry, the first breath, the inevitable fading of time into mortality. Consciousness, ephemeral and finite, emerges in a cosmos that may have neither start nor finish. This juxtaposition is humbling, even poetic. Our fleeting awareness flickers like a candle in a cathedral of infinite darkness. We mark moments, construct history, and seek causality, yet the cosmos itself may have no such framework. In this tension between finite experience and infinite existence, human life does not diminish but resonates. Perhaps our significance is amplified precisely because we are transient observers in an eternal theatre, capable of perceiving only a fraction of the performance, yet aware of its grandeur. Science, in its pursuit of understanding, has illuminated both awe and limitation. Observatorius, particle accelerators, simulations, and telescopes extend our senses to the farthest reaches. Yet the ultimate question, whether there is a beginning, a first cause, a moment of creation, may remain forever out of reach. The humility of this realization is profound. Knowing is a horizon that recedes as we approach, a mystery that enlarges with every revelation. It is here that philosophy and science converge, where curiosity meets acceptance, and where human imagination finds its proper scale amid cosmic infinitude. In this space, wonder is not a placeholder for ignorance, but a recognition of the majesty and inscrutability of reality. If the universe truly has no beginning and no end, then human existence assumes a different kind of poetry. We are not separate from the vast continuum. We are ripples within it, waves in an infinite ocean of time and space. Each thought, each breath, each action becomes part of a flow without origin, a movement that will never cease. Mortality and eternity intersect, finite minds within an unbounded cosmos, tracing arcs of awareness that mirror, in miniature, the endless unfolding of the universe itself. Perhaps our lives are not measured solely by beginnings or ends, but by the resonance we leave in the ever-continuing narrative of existence, a universe that neither starts nor stops, yet holds within it the quiet echo of every moment we inhabit. In the stillness of contemplation, one can imagine standing beneath the night sky, the Milky Way stretched across the horizon like a river of light that has flowed forever. There is no first star, no final collapse, only the vast continuity of space and time, the eternal hum of existence. And in that hum, humanity finds its reflection, fragile, finite, yet intrinsically bound to the cosmos. Our lives are brief, our history is fleeting, yet in the endless rhythm of the universe, each heartbeat, each thought, each moment of consciousness becomes a note in an infinite symphony, a reminder that even in the absence of beginnings and endings, we are part of something immeasurably vast, timeless, and profoundly beautiful. Here, at the edge of knowledge and imagination, the story of the universe merges with the story of ourselves. Perhaps we are not passengers in time, nor witnesses to a single moment of creation, but currents within an eternal river, ripples that arise, interact, and fade, yet remain forever inseparable from the flow itself. The mystery is complete, not in its solution, but in its capacity to humble, to inspire, and to remind us that our curiosity, our reflection, and our awareness are themselves integral to the infinite cosmos we inhabit.